Standard 8.1, given a graph of a polynomial function, identify global and local extrema, intercepts, domain, range, and behavior increasing and decreasing, concavity, and points of inflection. So essentially in this standard, we are being asked to analyze the graph of a polynomial function. Now for this particular function, it says sketch a graph of the given function, and my intention was for you to do it on the graphing calculator. So let's pull up a graphing calculator and put this function in. We have 16, we need to go to y equals to enter our function, and it's 16x to the third minus 19x squared minus 10x plus 53. And when we hit graph, we see that we really don't see a large portion of our graph. There's parts of our graph that are missing. So we need to adjust our window. I see our graph goes higher and lower. We can't see any peaks or valleys yet, so let me multiply. I usually go up by multiples or factors of powers of 10 rather. So I'm going to change this from 10 to 100, and we'll start with that. And if that's not enough, then we will change that. Oh, that is a much better graph. We can see all of it. Notice that there's a lot of empty space to the left and to the right of the graph. So maybe I will sketch my graph from -3 on the x up to +3 on the x so that we can see more of it in our window. So -3 to +3 and hit graph. Okay, that looks like a decent graph. So I'm going to copy this graph, and then we're going to find all these pieces of information that are missing. It says local extrema intercepts. So let me copy the graph first, and then we'll look at those parts. So here's what our graph looks like. Let me just glance at it one more time. All right, looks something like this. And we want to find the local max, min, and intercepts. All right, so local maxes occur at any peaks on our graph. So right here is where we have a local max. And we can find that value exactly on our graphing calculator. Here's how we do it. We're going to go to the calculate menu, which is above the trace key. So we press second. Let me turn this on again. Second, calc, and go to the option that says maximum. Excuse me. When it says right bound, we want to move our cursor to the right of that peak and hit enter. When it says, oops, I think I made a mistake here. Let me try that again. So calculate maximum. Left bound first, so move it to the left side of that peak here and hit enter. When it says right bound, move the cursor to the right side of the peak and hit enter. And notice you have two little arrows popping up, and your local maximum should fall within those two arrows. When it says guess, you're going to hit enter. And our maximum is at about -0.2 and 54.1. So let's indicate that here, -0.2, comma 54.1. And now let's find our local min, which occurs at any valley in our graph. So this is our local min. And we're going to find it using the same process. So again, go to calculate, go to option 3 for minimum. This time we're moving our cursor to the left side of the min, hit enter. When it says right bound, we're going to move over to the right side of the min, hit enter. We get those arrows. Our minimum should be between them. When we hit enter, our minimum's at about 1, 40. So let me indicate that on our graph as well. 1, 40 is our local minimum. We want to find the intercepts. So let's do our intercepts in green here. Our x-intercept first. How do we find our x-intercept? You're going to go to calculate, and we're going to go to 2 because zeros is another word for x-intercept. So if we choose option 2, it says left and right bound. Notice that our x-intercept here is between -2 and -1. So when it says left bound, I'm just going to type in -2. When it says right bound, I'm going to type in 1. Oops, I meant -2 and -1. Let's try that again. So calculator 0, our left bound -2, and a right bound +1. Nope, -1. All right, so our x-intercept is between those you can see on the x-axis when it says guess, hit enter, at about -1.3, 0. So -1.3, 0. And let's find our y-intercept here. And if we go back to our graph, notice your y-intercept is where it crosses the x-axis, or I'm sorry, where it crosses the y-axis, or where x is equal to 0. So if you go to the calculate menu again and choose option 1 for value, if you type in x equals 0, it will give you the corresponding y value, in this case 53. So 0, 53 is the y-intercept. All right, so now let's analyze this graph a bit. The x-intercept, there is only 1. We found our x-intercept to be at -1.3, 0. Our y-intercept is 0, 53. Our domain are all the x values that our graph encompasses. And since our graph continues to the left forever and to the right forever, and you can see that because the graph is widening towards the left and widening towards the right, our domain goes from -infinity to +infinity. And our range describes the y values that our graph is including. Notice that our graph goes up forever and down forever. And so our y values are also from -infinity to +infinity. Our local max we found using our calculator, -0.2, 54.1. And our local minimum we found as 140. Our global maximum is the highest y value on the entire graph. So if we look at our graph here, our graph goes up forever, so our global max is infinity. And our global minimum is the lowest y value on the entire graph. So if you look at the global minimum, or if you look at the graph, it goes down forever, so the global minimum is -infinity. So locals are like your peaks and your valleys, and globals are the highest and lowest on the entire graph. All right, so next up is increasing and decreasing. Our graph is increasing if as we travel left to right, the x values are, the y values are going up, or the graph is going up. So as we travel from left to right, the y values are increasing there because the graph is going up, and it's increasing here, and it's decreasing in this blue region. So let's describe these regions. Our first region where it's increasing is in this yellow region right here. And when we describe the region, we describe it with the x values that it's increasing through. The leftmost x value of this region is -infinity, and the rightmost x value is -0.2. Again, we're looking at x values here, throughout which the graph is increasing. So -infinity to -0.2. And our graph is also increasing here. And it's increasing starting at the x value of 1, which is where your local minimum is, and going to the x value of infinity. So again, this is interval notation that we're using to describe where it's increasing, and we indicate with the x values through which the graph is increasing or decreasing. So it's increasing from -infinity to -0.2, and also from 1 to infinity. And when there are multiple intervals, we connect them with a U that symbolizes the union of those two. We're including both. Decreasing is our blue region here. And so it's decreasing within what interval? Well, the leftmost x value of this blue interval here is -0.2. And the rightmost x value of this blue region is 1. Notice that the coordinates that we're using for increasing and decreasing correspond to the x values of your local min and your local max. And that should always happen because your local max and local min kind of define the boundaries between which it's increasing or decreasing. All right, so it's decreasing from -0.2 to 1. All right, then we have to talk about concavity and points of inflection. Let's find our points of inflection first, and then we'll do concavity. So I'm going to unhighlight all the stuff that I had highlighted for increasing and decreasing. Is this working? Let's try the eraser. And I want to re-highlight. Ooh, why is this not? Okay. Okay, so let me get our graph going again here. And we'll re-highlight using concavity as our discussion. So when your graph looks like this, when it looks like an umbrella, it's concave down. And when your graph looks like this, like a bowl or a smile, it's concave up. So in green here, it's concave down. And in purple here, it's concave up. Now the concavities do not overlap. So green is going to end and purple is going to begin. And it's really an estimation as to where that's going to happen. So I'm going to put that point right there, where one ends and the other begins. And that point is called a point of inflection. It's where your concavity changes. So where it changes from down to up or up to down. And this is an estimation. We don't know this value without calculus. We just kind of have to estimate. So I know the x value of this point is between the local max and the y-intercept, so between negative 0.2 and 0. So I'm going to estimate it at negative 0.1. And we know the y values are between the local max and this y-intercept, so between 54, is that what the local max was at? Yeah, and 53, so maybe 53.5. Oops, that's not where I wanted. 53.5. So again, your point of inflection is where the concavity changes from up to down. Now, concavity also includes like the walls of the umbrella or the walls of the bowl. So it's not just the one part that's curvy, but also the sides are included as well. All right, so let's fill out our information below. Our point of inflection, we said, was about negative 0.1 to 53.5. 0.1 to 53.5. And it was concave up in the purple region. So what x values does this purple region include? Well, it starts at the x value of negative 0.1, which corresponds to the x value of the point of inflection, and goes to infinity. So it's concave up from negative 0.1 to infinity. And it's concave down in the green region, and the x values that are included in the green region are from negative infinity to negative 0.1. So negative infinity to negative 0.1. So that's concave down. End behavior right now, we're going to simply state that the left end is down and the right end is up. And then is it continuous? Yes, because you can trace the whole thing basically without picking up the pencil there. And so it looks like increasing and decreasing got erased. We had it there earlier, but we have analyzed our graph to completion. Again, this is standard 8.1.